intelligent could basically apply to most of the stuff that we record on this show.
Definitely the last episode. That was a winner.
Oh my gosh. Yeah. So I think it just went live today. Maybe you haven't had a chance to listen to it yet, but it's
unfortunately.
It's a whole episode of Benjamin and I fighting to find the worst science/space joke ever.
And I think we found all of them.
There are none. There are no more. Oh gosh. For folks just joining us, welcome to another episode of Science Actually Presents The Nerd and the Scientist. As always, we have the nerd and the scientist, myself and Benjamin here. But we also have a very, very special guest who is both a nerd and a scientist, dare I say?
Sure, why not?
We have the incomparable Emily Kerrison joining us from Sydney. Emily is a PhD candidate at the University of Sydney. That's where I am. And Emily studies things with radio telescopes. That's what I do. But Emily works on really massive, or you could say supermassive objects in space called AGN, Active Galactic Nuclei. Emily, welcome to the show.
Great. Thank you so much for having me. Very glad to be here.
Yeah. I'm so glad to finally get you on intentionally. I feel like back in season 1, you made a couple of like Easter egg cameo appearances when you and I used to share an office.
Yeah, for the long-time listeners, long-time watchers, you might recognize my face. I unintentionally ducked in a few times, but this time I'm meant to be here. It's good. I've been invited.
Woohoo!
Here, I have this invite. It's real. I'm allowed to be here. Oh, wow. Cool. So I'm sure Benjamin has loads of questions. I just have one question that I have to start with. And I'm so curious. I feel like I've never really asked you how it was that you kind of pivoted / chose from your undergraduate degree, which is like science, but also art science, and also like the classics like Greek, how you got from that to where you are now. So what's like the origin story of that decision?
The origin story. Well, I got bit by a spider and then no.
Oh,
so
she's a nerd. Yes. That answers the questions. I think we're done here. I think we're good.
Yeah. That's it. That's a podcast. Very happy to talk about stuff like that. So yeah, I did a combined undergraduate degree. I finished school, didn't know what I wanted to do. I was like, hey, I like history, but I also like science. So let's do both. And at that stage, you could just do both. I was like, cool, I don't have to pick. We'll just kick the decision down the road. So that's kind of what I did. Did some really cool units at university, did everything from looking at some of the earliest written Greek texts we have, which are these really cool poems that were sort of written down, but we know had been passed on for centuries before that as kind of an oral tradition. So people would memorize them and then pass them on to their kids to memorize. So I studied stuff like that. And then on the other hand, I was in physics and we were looking at, quantum entanglement and looking at how stars form. So it was kind of very separate areas to be studying at the same time. But then I kind of got to the end of my degree and I was like, you know what? I want to see if I can combine these in any way. So I actually did a thesis looking at really ancient understandings and interpretations of science in kind of the Greek world and how that manifested in lots of the texts we have now. Because obviously what we have left from so much of history, from the Greek and Roman history, but also all around the world, is what people found interesting in later periods. Often that was not the science. Often it was the poetry because it sounds nice, and it's easier to remember. So that tends to be what survived, and the science kind of survived in bits and pieces through that a lot of the time. So I was really interested in why some of it made it into the poems and, how it might have been received. Anyway, so I did a thesis on that. That was all very cool. But while I was doing that, I found that as much as I love the classics and the history, it was really understanding the science and the new discoveries that was super exciting to me. So I then was kind of looking around, trying to think about what to do. And I actually managed to land a summer job at CSIRO, Australia's National Science Agency. Got to make sure to get that full title in there. Otherwise, I'm sure CSIRO comms will have things to say.
Oh, yes.
Kovi, I'm sure you've heard about that. But yes, so I landed a summer job at CSIRO, and I actually got to work with a team doing things in radio astronomy, and it was really cool seeing how they could do the science, but they were also a little bit closer to the instrumentation than what I'd seen in kind of my studies. Because often, when you're studying, you need to learn the basics. But that means when you're learning the basics, you're kind of divorced from the cutting edge stuff that is happening over in research. So it was nice to move into this space where I could actually be with these researchers who were doing the active research on the science and also the development of the instruments doing the science. And I was just like, wow, this is awesome. This is the cutting edge of human knowledge, basically. And it kind of just went from there. I sort of, I was like, I want to do postgrad in this. Then I found a supervisor, and then it all kind of snowballed, and here I am talking to you guys.
Well done.
I love it. That's so
Love
great.
the whole blending of arts and science, which is huge. It's a very positive thing. It makes it what's the word? I don't know what the word is, but it makes it easier to convey things to the general public when you have an artistic flair on it, and it just makes it more appetizing. I love that.
Thank you. Yeah, I hope so. I mean, I do remember when I was writing up my honors thesis in physics, I had sort of presented it to my supervisors as a first draft, as you do, and I was a little bit nervous. I was, waiting for a week or so for them to get back to me, and then they got back to me and they were like, Emily, this is great, but it's way too conversational. There's way too much flair. You need to tone it down. I was like, oh, yeah, fine, I'll make it boring.
Oh God, I've been there.
For the public. Yeah, great for the public, less good for scientific publications, but
It's tough, because I guess when you're writing for the public, you're trying to be a bit more descriptive and you're trying to engage people with your language indirectly and kind of tell a story. Whereas with scientific writing, it's like, we did this and we made a mistake and then we accidentally discovered the secret to the universe. Like bang, bang, bang. It's just like a bunch of short sentences, just like one after the other, very matter of fact. So yeah, it's definitely a tough line to walk. But wow, that's so cool. And I feel like, Benjamin, you were not expecting as much of the non-science in this origin story. I could see your face during that. Oh, okay.
Oh yeah. Well, I am that public that you mentioned that one that likes hearing stories. That's great. I like the matter of fact phrasing of things, but
yeah.
You need the best of both worlds.
Yeah, both definitely.
All right, so the thing that Benjamin's been dying to talk to you about has got to be AGN and Quasars and dying, literally messaging me for the past week. I can't even consider how we could leave this question out. But yeah, I feel like, Benjamin, you have like so many questions. So I'm gonna stop talking.
Well, no. Well, here are all. Okay, this is. I've been reading as much as I can in a week to get up to speed to what you've been doing for years. So
you might know more than me.
We are on equal footing now. All Blazars are Quasars, but not all Quasars are Blazars.
Amazing. Yes. Very good.
Yeah!
So would you like to explain to the audience the difference between a Blazar and a Quasar?
Blazars are just Quasars that are pointing at us.
Yeah. Yes.
That's it.
Exactly. Yeah.
That's the only thing. That's it.
Yeah. Amazing.
That's it. We're done.
That's it. Yeah. Done. Again. End of the podcast.
I'll take my degree, please.
But yeah, I guess for those of you out there who are thinking, what the heck is a Quasar and a Blazar? So this is really a term describing supermassive black holes at the centers of other galaxies. So we have these really big black holes, many millions of times the mass of the sun, very, very compact, but they're so dense that they're quite spatially big as well. They have so much gravity that they're pulling in lots of dust and gas and matter that's swirling around them in an accretion disk. And we're pretty sure that's basically a 2D CD-shaped disk, for those of you out there who still listen to CDs. So we think they've kind of got this CD of matter swirling around them, and it's being accreted onto the black hole. And there's so much high energy physics going on there that we get energy being emitted because this matter is being compressed as it's being sucked into the black hole. Part of these emissions that we get are actually two massive jets of plasma. And we think that these propagate out perpendicular to the CD disk. So you kind of have something like a spinning top, except the plasma is coming out both top and bottom of this black hole. And that's what we see in the radio. So when we see this really, really bright excess emission, we tend to call these supermassive black holes quasars. So you see the plasma in the radio, you see all sorts of optical light as well coming from the accretion disk and all the fun stuff going on in there. You basically see it all the way through from radio right up to X-ray and gamma rays, because this is such an energetic environment. There's so much happening in here. It's just emitting every which way possible as this matter is being sucked into the black hole. So in the radio, I'm looking at these plasma jets that are coming out along one axis. And as you said, Benjamin, if they come out along an axis so that we can actually see the full extent of them, like we're looking at them on a page, then it's a quasar. If their turns kind of face on so that the jets are coming out along our line of sight, it's a blazar. And these blazars are really interesting basically because you're looking right down along the barrel of the gun, basically, of the plasma jet, which means that any tiny variations you see in there are amplified many, many hundreds and thousands of times just because of what we call a beaming effect. So the radiation is pointed towards us, so any kind of Doppler effects that you see are really at their maximum along this axis. So things are accelerated or decelerated as much as they can be because they're pointed directly along our line of sight. And that's when things get really crazy if you look at these things over time. They're varying like, hundreds of percent. It's really, really quite shocking that you can actually get this variation that's so extreme. But it's because we're looking at things right down the barrel of the gun where that energetic physics is really happening. It's super exciting.
Just as a disclaimer for people listening at home, whatever you do, do not look down the barrel of a gun, especially not a gun that's coming out of a supermassive black hole shooting very energetic plasma directly at you from across the galaxy. Not recommended.
But yes, very important PSA. Thank you, Kovi.
Just in case, just in case. It's so cool, though, that like the more you know. That's a fun fact for you. It's really cool, though, that like we've actually figured out that these two things are the same, because another like historical tidbit is that the name quasar comes from quasi-stellar, because basically people used to think these things were stars, up until the 1960s or maybe even 70s. Like people weren't really sure what was going on here when they would see these things with the radio telescopes. And so to not only understand now, okay, this radio star is actually a quasar, and this quasar is actually a galaxy, and that's related to a blazar just by virtue of, our relative angle of how we're looking at it. It's really cool to see like the naming conventions actually converge to one physical situation or scenario that we can like understand and be like, aha, that's what it is. Now I get it.
Yeah, absolutely. It's really cool. And to add to that, I think I've got this right. Hopefully someone in the audience is going to like shout at their screen if I'm getting it wrong. But I actually think the term blazar, again, has a bit of a historical significance. Kovi, have you heard about this one? So I think it comes from the original blazar that we know of was called a BL Lac object. And so then everyone saw this thing and they're like, oh, this is a one thing. We'll call it BL Lac. And then, they thought it was this really cool, unique thing. And then they looked, they were like, oh, actually, no, there are a few of these things. We can't call them all. And so a lot of them were just called BL Lacs. We'll just copy the name, keep it easy. But it got to the point where there were so many of them that were like, well, maybe these look like quasars, but they're BL Lacs. So then I think the names kind of got smushed together as a portmanteau, and that's where we get the blazar term. It's a BL Lac quasar.
I did not know that. I thought it was it's like a blazing bright thing. That was always my assumption. I did not know. I knew about BL Lac type AGN. I didn't know that. That's so cool.
I think that's where the name comes from. I hope I haven't just made that up. I'm going to go away after this podcast and do research and possibly be very embarrassed, but that's okay.
No, we are going
it's a cool story anyway,
establish it as fact, as first reported here on this show, because we need all the cred we can get. I'm taking it.
Oh gosh, Benjamin, you were smiling throughout that explanation. I think you came across some of these terms during your prep.
Yeah, I Nothing. Well, I had it. I asked Kovi for if an idea for a joke was good, and he sent me a gif of someone being showed the door to leave. And I was gonna say I like my AGNs like I like my coffee, BL Lac. And
Oh yeah, nice.
I thought it was
Yeah.
funny. She thinks it's funny. She studies it, Kovi. That's 2-1. You lose. It's funny.
This joke would have been perfect for last week's episode.
Oh God, last
It
week's
has a
episode is
place.
going to resonate for a while.
Maybe you could make it a new segment on the show. You know, a terrible joke for every topic.
No, we ran out.
Oh, that's it. They're gone.
We have quenched the resources, the pool of possible bad jokes.
Anyway.
Maybe I can do a quick radio ad before we continue with these quasi questions about quasars.
That was brilliant.
Hey, Benjamin, have you ever dreamt of owning your own piece of the cosmos?
Daily.
Daily. Do you want to leave your mark on the universe?
Yes.
Well, that's great, because now you can, with Quasi Quizzes Quasars. That's right, folks. At Quasi Quizzes Quasars, we offer you the exclusive rights to name your very own active galactic nucleus. Tired of naming stars after your ex? Why not go bigger? Name a quasar instead. So what are you waiting for? Call 1-800-QUASI-AGN today. That's 1-800-QUASI-AGN. Quasi Quizzes Quasars, because the universe could use a little more quasi.
Is quasi spelled with a Q or a K? I hope it's with a Q. That's beautiful.
I'm gonna let you spell it however it resonates best with you.
Yes, sir.
I'm really curious now. How does you've got to pay for these things, right? How does the cost scale? Is it with mass? Is it with angular size?
Ooh.
Like that could be a very expensive venture there.
I mean, the cost scales with Schwarzschild radius.
I know what that is.
Oh gosh. Okay, so Benjamin, I feel like we've spoken about AGN and we've gotten your BL Lac joke in there gladly. Yes. I'm glad that we got that. But Emily was just talking about how when we're seeing the Blazar, we're seeing like the jet face on and it's coming towards us. We see these really intense, or really quasi, if you will, variations in the brightness. And I know that you had some questions about changes in the radio that we were seeing and whether or not they were real or not.
Oh. Is that the radio scintillation I'm trying so hard to figure out in all the reading I was doing? Is that what that is? And when you're looking down the barrel of a quasi quasar gun, that's where the radio scintillations are?
Emily, I'll let you take this one since it's your area of expertise.
I appreciate the segue that we're going through here. Okay, yes, we're moving on to scintillation now. That's what I'm getting from this kind of...
In preparation for the show, whenever I get nervous, I always message Kovi and I have conversations, and he's so kind to me. He's so kind. And I'm like, I don't understand this. I'm afraid I'm not going to be able to ask proper enough questions. And he says, don't be afraid. Just say, can you explain it to me like I'm a 5-year-old? And I was like, Kovi, come on. Explain it to me like I'm a 10-year-old. But yeah, I was trying to find out what radio scintillation means. I know that's what you're specializing in, and I just couldn't process it, but now I know.
Yeah.
Elaborate, please. So that Kovi can catch up.
Yeah. I see. Yeah.
Yeah.
So scintillation then. Yeah. So we've talked a lot about looking down along the line of sight of the radio jets, and we see variation there, and that's sort of in the jet. That's blobs of plasma that are coming out. Not uniformly, they're all kind of clumpy and blobby, and that's why we see variations in the Blazars. But the other kind of variation that we can see is this scintillation. And so what that's actually caused by, it's when you have light waves that are coming from the source towards the Earth, and somewhere between leaving the source and arriving at the Earth, they actually pass through another clumpy medium. So that can be the clumpy plasma that's kind of wafting around the galaxy. It can be the plasma that is streaming off the sun, or it can actually be at different wavelengths. It can actually be the atmosphere of the Earth as it changes densities due to fluctuations in temperature and pressure and wind movement and all that kind of thing. And so as these light waves travel through space or through the atmosphere, they hit these little patches of differing density and they start to refract. So the different parts of the light wave bend because it's passing through different mediums of slightly different density. And that basically means that by the time they reach us, we have little patches of interfering light because they're slightly offset, their phases are slightly offset from each other. So you can kind of think of that like the light's arriving at slightly different times compared to when it all left the source. And that actually causes a twinkling. So in the optical, we see that if you look up at the sky at night, you can see stars twinkling. And that's exactly the same phenomenon that we see in the radio. It's just that it's caused by a different clumpy medium. So with the stars, the twinkling is caused by the light from the stars coming through the atmosphere, and the atmosphere density is always a little bit fluctuating, a little bit changing. But for these galaxies that I'm looking at, as I said, it's often that the light is passing through the plasma that's kind of permeates the galaxy, or the gas that permeates the galaxy, or it's passing through basically the matter streaming off the sun in kind of the solar wind. And that's causing the same phenomenon just at radio wavelengths. So we actually see the radio frequencies twinkling as well. So we get these galaxies twinkling in the same way that stars twinkle at night. I think it's really sweet.
That is.
And you see there the connection between the arts and the science. I mean, that description was just poetic, but also scientifically accurate. I love it.
Oh, thank you.
See?
Benjamin, does that answer your question?
Yeah, it does. I had electron density and ionosphere in my notes, and she nailed it.
Amazing, well. Amazing.
I had it in my notes. I didn't exactly know how to put it together. She did that, which is wonderful.
Well, it is my job, to be fair.
Well done. Well done. Well done.
Thank you. Thank you. I passed.
Here, have a degree.
Amazing. Yes.
All right, Benjamin, what other notes or questions do you have? Now, like, we have to make the most of having this expert here with us.
It's a silly question, but the term active galactic...
No such thing as silly questions, just silly people.
I can push that. The term active galactic nuclei implies maybe there's an inactive galactic nuclei. Is that a thing? Or I would assume, are all the galactic centers kind of... I would assume they're all bubbling with all sorts of black holes and quasars and junk. They're the centers of galaxies for crying out loud.
Yeah, that's a really interesting question. So we are pretty sure that every galaxy has a supermassive black hole at its center. There are some really small dwarf galaxies that probably don't, just because there's not enough stars and matter collecting to suggest that there's a big gravitational well at the center. But we think almost all sort of average size, whatever average means, average size galaxies have the supermassive black hole. Kovi, I think there might be one potentially that we think doesn't. But that's really going into the deep recesses of my memory trying to recall that. I don't know, maybe something jumps out to you. But anyway, I think there might be maybe one that we've seen that we think doesn't. So everything has a supermassive black hole, every galaxy. But active galactic nuclei, you're right. The name active suggests that there's an inactive. And we do know that active galactic nuclei go through cycles. We call it a duty cycle of activity, where they're super, super active and then they're a little bit more quiet. So, for example, one easy way to see if there's an active galactic nucleus is to look in the radio, which is conveniently what I'm doing. So yeah, right. Good choice on my part. I didn't know it at the time, but in hindsight. But yeah, so we can look in the radio and we actually see that a lot of galaxies out there don't have very bright emissions in the radio. So that suggests that even though there's a supermassive black hole there, they don't have the plasma jets that are shooting out and producing these really loud radio emissions that we see. So we definitely think that there is some sort of duty cycle going on. Whether every supermassive black hole will be active at some point in its life, I don't think we actually know that yet. Again, Kovi, please jump in if I'm talking rubbish here. I
mean, no, it sounds like everything's all right. Like,
yeah, tick of approval.
All I'm thinking in addition to that is the idea of quenching, right? Where at a certain point, a galaxy will run out of material to feed, like that central engine of the AGN. But I don't know, is that like maybe that's just a cyclical thing as well that happens in the duty cycle rather than a long-term phenomenon.
Yeah, so again, I think this is actually still a bit of an unknown. So we talk a lot about there being a duty cycle, that these AGNs switch on and off, so they're active at some points and they're not active at others. But why they actually turn off, why they turn on, I think a lot of that's still an open question. So we see sometimes a lot of the nuclei that are active tend to be in galaxies that have collided with other galaxies in the past. So you've got this kind of massive, you know, interaction that's happening over, we would say parsec scales, but many millions of kilometers, as these galaxies smash into each other and they exchange stars and gas. And there's something about that process of interaction that kickstarts these galactic nuclei and makes them active so that we can see them in the radio. But whether that is something that happens over and over again, or whether it happens once and then something, as Kovi says, that they run out of stuff to keep feeding them and then they turn off and that's it, or whether this is something that happens, like once every 5, 10, 15 million years, I don't really think we know yet. And a lot of that goes back to the fact that as astronomers, we're looking at the universe at a snapshot in time. So that snapshot changes because you can look further back in time by looking at higher redshifts. But ultimately, every galaxy, we only ever see it at one point in time. So it's actually really hard to connect the dots between all these different galaxies and work out what a full life cycle looks like from all these individual snapshots that are in slightly different environments. So that was a really long way to say it's an interesting question, and I don't have one set answer for you.
Definitely not a silly
How
question.
can we tell something like that massive in the center of a galaxy can switch on and off, like you said? And then you explained it right away, because we're looking at a snapshot in the time scale of millions of years. So,
I mean, it's quite impressive to consider the fact that like we're getting, like as you mentioned, it's still somewhat of an open question, but we're getting a good idea of how certain things in the universe work when their lifetimes are several orders of magnitude longer than human lifetimes. In fact, they're orders of magnitude longer than the entire history of human civilization. And so the fact that we can, like you said, Emily, by looking further out into space and therefore further back in time in the history of the universe, can like indirectly figure out how things behave over millions or billions of years, despite the fact that most humans will not live for that long.
Yeah,
Well,
I mean,
most.
we're space detectives, right?
Yeah. I love that. Every time, yeah. Oh, all right, cool. I feel like we're delving into the secrets of the universe. Benjamin, you're looking at your screen. You have more questions.
No, I'm actually kind of running out.
Oh God.
Your turn, Kovi.
You have quenched your quasi questions about quasars.
I've quenched my quasi questions about quasars.
Oh wow. Yeah, I've actually been reading recently about the history of radio astronomy, the work that was done by some great people, both kind of moving from the UK to Australia following World War II, folks who had worked on radar in World War II and then moved to Australia and built all sorts of really impressive radio telescopes. And it's, as you mentioned, it's like the forefront of science. It's not just like, oh, let's just like, we know what telescope we need, so we'll just like build it and then we'll look at the thing and we'll measure the data and we'll take the results and write the paper. No, they're like this work that was done by folks like Robert Hanbury Brown. It was like, you have to invent a whole new area of science in order to invent a whole new type of telescope, in order to measure something that's never been measured before, right? So like a lot of the work that they were doing, they were measuring the angular size. So that's like how much actual size something takes up on the sky of quasars, which had never been measured before. I mean, they haven't even, at that point, historically, if you go back more than 70 years, we didn't know on the sky what the size of a star was. I think Galileo had tried to do this by holding up a piece of silk and measuring a star, or if that tiny thread, that strand of silk, would cover a star as it rose above the horizon. He's like, oh yeah, I guess the size is about 5 degrees, and that's That's like 10 times the size of the moon on the sky. Like that's not like it's got to be smaller than that, but it's not a helpful upper limit. And so this work that was done by Robert Hanbury Brown and others using Australian radio telescopes and using other sort of wacky intensity interferometers that used optical light, we're doing these first measurements, and that helped us figure out what quasars were. So I'm so impressed to see, like, Emily, how your research fits in this like overarching story that, like, we knew so little less than a century ago, and we've gone from like, oh, it's a weird radio star twinkling, we don't know what it is, to like we understand so fundamentally, like that we know so many properties, and there's still so much more to discover. So I don't know, that was more of a rant than a question, but like I'm just blown away by this.
Yeah, I mean, I don't worry, I love a good rant, but I totally agree. I think it's amazing how far we've come in such a short amount of time, really. You know, relatively speaking, radio astronomy is quite a new field still. And now we're talking about, you know, looking back to cosmic dawn, when light first came into the universe, or when, you know, matter was first reionized by the very early galaxies. Like, that's really cool progress that we're able to make. Yeah.
For sure. What would you say are like the main things that you know want to see? Like, what would be the questions that you want to see answered by your field in the coming decade?
Whoa, that's a tough one. Okay, so I guess talking about radio astronomy, AGN, I mean, maybe going back to what we were talking about before, I think really pinning down what this duty cycle of AGN is, trying to work out whether every galactic nucleus is an active galactic nucleus, and whether that happens once in its lifetime or 50 times in its lifetime. I think knowing that would be really interesting, because that would tell us something really quite fundamental about the universe. You know, are all galaxies active in some sense at some point in their life? Is that the same now as it was, you know, 5 billion years after the Big Bang? Is it all, are we, you know, part of one cosmic soup that's pretty continuous and pretty uniform across that time, or are things really dramatically changing? Is there something really, really unique about the time we're in now and about the galaxy that we're in now? Yeah, I think that would be really exciting.
Well, as far as we know, the galaxy that we're in now is the only one that has tequila, and I think that's pretty unique.
That is true. That is true. That's where I keep all my stuff.
In the Milky Way. Oh my gosh, that's amazing. And would you ever consider doing astronomy not at radio wavelengths? I feel like that's like a forbidden question.
Whoa,
Oh,
yeah.
really? Ooh, taboo science question.
Yeah, I mean, it's really interesting when you think about sort of the different wavelengths. And I think maybe part of this goes back to what Kovi was saying earlier with the birth of radio astronomy. It really came about after World War II, where you had all these engineers who had worked on radio communications, kind of all secret hush hush stuff during the war, who then wanted to actually do cool science with the technology that they developed, because they heard all this random noise and they worked out it was coming from space. And they wanted to find out why it was coming from space, what was making the noise in space, and that was really how radio astronomy was born. And that's pretty different to pretty much all the other areas of astronomy, particularly optical, because optical has this really centuries-long history of, you know, looking at the stars, looking at nebulae, looking at these really pretty things with your eyes, and kind of thinking deeply about what they might be. Whereas radio, in some sense, was kind of started by accident. People heard this noise during the war and they're like, hey, that's kind of weird. So there is, I think this divide has persisted a little bit in modern astronomy, where you kind of have radio astronomers who work on our data and maybe pull in extra multi-wavelength stuff to help us. And then you have the other astronomers who do the same thing on the other end, and you kind of don't cross over all that much. But would I make the leap? I don't know. I actually started very early on looking at stars in the optical. Oh, I was a stellar person. Crazy. I know. But yeah, I mean, I think it could be interesting to maybe dabble a bit more in other wavelengths. I think the high energy stuff is really, really exciting and really interesting too. But the difficulties you have there is you're looking at single photons because everything is such
God.
high energy. It happens so rarely. You've got to care about every single photon, which is such a different approach to the observations what we have. We're just kind of drowning in this radio data, and then they're looking at counting individual wave packets of light as they arrive. I think it would be a cool adventure, but I don't know if my brain's set up to deal with that.
No.
It's like just so like to really drive that point home, Benjamin, when we are like, you know, talking about an AGN that we have radio observations of, but also some other telescope looked at it in the infrared. And then you have infrared measurements that are in units of magnitude, and you have radio measurements in units of Janskys, named after Karl Jansky, one of the fathers of radio astronomy. And so you have this thing of like, oh, well, the brightness is 30, but what units of brightness is that in? And you have to like play a bit of a game to convert the units, and so that, you know, infrared and radio can be compared. But with X-ray, 30 literally just means there are 30 photons. 30 individual light particles hit the detector. That's it. And I think 30 is actually quite high for an X-ray detection.
Yeah, for an AGN for 30, everyone would be like celebrating in the office. That would be exciting, you know.
Dancing in the streets.
Yeah.
So that's funny. That's a kind of weird number. Okay.
Yeah. Speaking of weird numbers, I know another thing that you do with respect to AGN are looking at the number or the brightness numbers that you get for AGN at different frequencies, at different wavelengths. Could you tell us maybe a little about that and like why that's useful and what we're getting out of it?
Yeah, sure. Yes. So, you know, Kovi and I work in radio, but there's a lot of frequency space in radio. It goes from tens of megahertz right up to sort of hundreds of gigahertz. You're sort of getting into the sub-millimeter regime, you know. So that's kind of borderline, but anywhere in there, that's you know, orders of magnitude in frequency space. It's quite a big space to explore. So historically, people have tend to pick sort of their favorite frequency to look at things, and their favorite frequency often is because that's what their instrument can see. So, which, you know, understandable. It's good to pick a favorite that you can actually look, you know, detect. That's good. But now we're kind of at a point in radio astronomy where we have not only a bunch of different instruments looking at these different frequencies, but we also have new instruments that on their own can look at a wide range of frequencies. So it's really opened up kind of the parameter space that we can look in to kind of understand what's going on out there. So part of my work at the moment is trying to compile all of this information at different frequencies for these individual AGN and see what that can tell us about them, as opposed to just using one frequency measurement. And so we're actually finding these really interesting patterns emerge with these AGN, where they will have very kind of characteristic variations that follow a nice smooth curve as you look across the frequencies. And that's quite nice because that actually can tell us something about kind of the gas density in and around the AGN. It can maybe tell us something about their size as well, which is super exciting. And it just means that basically we have all of the data is kind of already out there, because radio surveys have been going on for decades now. So we actually can basically get this information for free at the moment. We can just pull all the data together, work out what belongs with what, and then we kind of have this extra set of information just by putting it all together in this new way, which is, you know, it's really exciting. It's always nice to get free extra information out of data you already have, rather than going through the process of proposing a new project and then waiting 6 months to hear back whether or not it's successful, and then waiting another 6 months to get your observations, and then another 6 months to do the data reduction, and then wow, 3 years have gone by, you know. But the data's out there. I'm just making use of what's freely available. It's great.
It's fantastic.
Love it.
More learning is done faster. I love it.
Exactly. Yeah.
Oh, that's so great.
And you know, I think
and it really is. Sorry.
Oh no, please.
Go on. You're the guest.
Well, thank you. I have right away.
A gentleman.
Yeah, I guess I was just going to say, at the moment, a lot of discussions that we have in radio astronomy are about how much data we're getting and how to deal with it, because we're producing all of this stuff. We have kind of a responsibility to store it in a way that is accessible for the future, but also that's energy efficient, because we need to care about our energy consumption as scientists living on a planet that is getting warmer. So I think if we can find new ways like this to combine the data that's already out there and get more information out of it, it's really, it's making us better scientists, because we have to think about new ways to use the old data, and it's also making us in a lot of ways kind of more responsible with our data, because we're extracting as much out of it as we possibly can.
Yeah, that's really interesting. It kind of ties in with what I was going to say, because I was going to make a comment about how, early days of radio astronomy, people, as you mentioned, they would like, spend 6 months planning or proposing to get data, and then they would spend 6 months like dealing with reducing that data, and then you could spend a whole PhD just dealing with one observation, one data set of one thing. And we kind of transitioned out of that at some point in the maybe the early 2000s or in the last decade, to this place where we're like swimming in data. And some telescopes now, especially like the ASCAP telescope, the Australian SK Pathfinder, it can do an observation of the entire sky in like a couple of weeks. And so if you have a serious data quality issue, you might just say, stuff it, will observe again, rather than really getting the most out of the data. And I think it's a really good point that you're making about how we're kind of finding the third stage of that evolution, from like struggling to get the data to being spoiled for data, to now really trying to be aware of making the most of what we do have, because there are second and third order consequences to being little bit too blasé about how quickly we re-observe, or Blazar, as Benjamin might say. I could see in your face that that's what you were thinking.
I was about to write it to you in a side note, Blase Blazar. Oh.
Same wavelength, same frequency. I love it. Amazing. Emily, thank you so much for taking the time to join us. Was there anything else that you wanted to share with the audience? Any final message, or just to let folks know where they can find you on the interwebs, if they're so inclined?
On the interwebs, yeah, sure. I have a very inactive Twitter account, but you're welcome to follow me and hit me up. It's just at Emily Kerrison. I managed to get my own name, which is cool.
Wow, nice.
I know, right? Where else can you find me? I mean, I'm on LinkedIn, the professional network. You can find me on there. I'm also just Emily Kerrison. But final message to people, I guess, stay curious. Think about, ways that you can have these kind of cool conversations with people. I'm so grateful to you guys for inviting me on to talk about my cool science and to hear about, your thoughts about the universe. So stay curious, people.
Oh, thank you. That was wonderful.
I love that.
You, Kovi? Where can they find you? Yeah, and
people can. Me and my beautiful face. Don't know what you're talking about. People can find me at Fun Fact Science on all the good social media platforms, as well as all the bad ones. And yeah, all science is cool science. That's what I have to say. Benjamin, where can folks find you? Where can they find this show if they're so inclined to watch previous episodes?
Oh, first of all, I hope they do. And they can do so by looking up Science Actually on all the, what Kovi calls the time wasters, the good ones and the bad ones: Facebook, Twitter, Instagram, LinkedIn. You can find this video on TikTok and on YouTube, and all of our past episodes as well. And keep an eye open for Quasars Quasars t-shirt, which is I already have some notes. I'm gonna mock that up. I'm gonna make that available to you good people.
Amazing. Well, thank you, Emily, again for joining us, and thanks everyone at home or in the car or in the bathtub, wherever you're listening or watching. Thanks for joining us for another episode of Science Actually Presents